Ow.
Hello and welcome to CMS. So we are here in just outside of Geneva, Switzerland, and we're talking to you from the CMS control room. So my name is Andres, and I am a colleague of Matt's. I hope to show you guys the some of the facilities here at CMS and the underground facilities as well. So just to give you an idea what to expect today, we were actually hoping to show you the detector, but there was an intervention that finished a bit earlier than we expected. So this morning we already had the cryogenics that were involved in the intervention. This is all recovered by the morning, so there's now beam in the machine. Actually, that's not entirely true. There is commissioning activities, however, ongoing. So there's no beam, but it also means that there's no access because of these optic commissioning activities. So that's what's going on with the LHC right now. I can, of course, talk a little bit more about the schedule and the short-term and also long-term schedule as we go. So while we are here, it's a little bit, I'm trying to buy a bit of time because our colleague Sonia is not here just yet. So perhaps we can go around the control room and we can give you an idea of what maybe before we do that, we can quickly show you a picture of the area here in the vicinity of Geneva. So what you see in the photo, you can hopefully see the lake of Geneva, and in the very far background, you see the this is Mont Blanc, so you see the Alps in the background. And of course, this yellow circle is supposed to represent the LHC tunnel. So the LHC tunnel is 26.6 kilometers in circumference. I believe that's like 17 miles or so. And something interesting is you can see, hopefully, the Swiss and French border. So that is the dotted line that starts here on the left. And you can see that the main CERN site is just something like 20 minutes. So it's here, just about 20 minutes outside of Geneva. Yeah, so I will discuss a little bit about the LHC as we go along, but maybe for now we can uh, show you guys our new control room. So the past year, I would say, we have moved to this new control room, and this is a new small building. And this is where we have our crew on shift 24/7. We have at least two people that are here in person. We also do have some shifters that are doing their shift remotely, and we have 3 shifts per day. So the two most essential shifts are the technical shifter. You can see the desk right now. The technical shifter is responsible for safety, human safety, but also detector safety, and also other things like detector controls. So and also responding to any kind of situation. They're responsible for the access to all of the underground areas, and just generally monitoring something that might be interesting that since we're here, maybe show the actual detector. So that we have some cameras. Unfortunately, we can't go into the experimental cavern, but you can see a little bit of CMS. These are live images from the detector. And I will try to hopefully, this is a nice picture. You can see uh, the sort of the point of view from the top of the detector from where the beams are coming in. So in this picture, you can kind of see the cylinder, and the beams would come in from the direction of the camera into the detector. And we'll talk about a bit of what's going on inside of CMS. But yeah, I just wanted to show you guys what it looks like right now. And our detector, of course, is let's say, closed, we can open up CMS. I'll talk about that also in a bit. But right now, it's basically ready to take collisions. And we hope to have collisions later tonight. And yeah, so maybe just to move on, we have all of this monitoring going on with the technical shifter, and then this is the shift leader desk. The shift leader is the captain of the boat, so they are responsible for safety on site, and they are responsible for the data taking. And there's a million things to keep track of. Just you can see some plots here. This is, I think, monitoring the RAM usage, so the memory usage of many of the machines. And then on the top left, you can see, I don't know if Noemi can just get a bit closer so you can see the DAQ. So this is a summary of the data acquisition status. And this has a list. There's all these green boxes that say in. So to the left of those is the names of many of the subsystems that make up CMS. And the data acquisition is basically taking, let's say, funneling the data from all of these systems, and then basically preparing that data as it goes through multiple stages, including the trigger. There's multiple stages of the trigger, and then finally the transfer of the data to the main CERN campus. And then from there, the data gets distributed around the world. But this is, here in this room is where we have the actual data acquisition, and we'll get to see a bit of the hardware that is responsible for the the merging of this data, if you will. So yeah, just to the right, you can actually see the shift leader's station, the DAQ shifter station. And again, even more things to keep track of. So there's lots of monitoring that takes place, and a lot of responding to issues. As you may imagine, there's any number of issues that may come up at any time, and we need to respond to them immediately. So there's a lot of we have people that are on call, so experts that are on call, and they respond to any problems that we may have with the data taking. And this often, sometimes these problems are easy to solve. Many times they're not so easy to solve. And there's, of course, issues that may come up at 4 in the morning, and people have to wake up and quickly try to solve any issues that are going on. And again, the data acquisition system is in charge of data taking in general. So it's collecting the data and then making sure that it's processed through the multiple stages of the trigger, and then finally the transfer of the data. So we have a few more shifters. I've already mentioned this trigger. When we talk about a trigger, we're more or less referring to a filtering system. And in these kind of experiments at the Large Hadron Collider, the data rate is far too large for us to handle all of the data. We really have to be selective, and we have to filter the data that we consider interesting, which is difficult to converge on what that is. Like, what kind of data do we want to collect, and how often do we want to collect it? But yeah, this trigger system is essentially selecting from a menu, let's say, of the type of data we want to collect. And you can see that there are some DQM plots here. So another important aspect of all of this is taking good quality data. So DQM stands for data quality monitoring, and you can see that there's some green and some red. Generally, we want things to be green, but things are quite complicated because there are known issues, there are known exceptions, right? So it's not so simple as red or green. There's a lot to try to understand, right? And just to give you a simple example, we expect to go to collisions later tonight, but we're going to be colliding at a let's say uh, at a lower luminosity, a lower rate of interactions, if you will. than usual. So it means that some of the plots might look less populated than usual. So that's the sort of thing we need to take into account. So we are now gone around and we have some of the event displays here that are a bit interesting. So this is sort of a representation of what the data looks like when it shows up in the detector. But again, something to keep in mind is what we're doing is we're colliding generally protons together, and we look at the aftermath of the collisions. But what that means is we have many, the debris of the collisions hits the sensitive parts of the detector, and we'll talk a little bit about what each of these parts of the detector do. But we have to basically play detectives and look at all these signals that are left behind, and then reconstruct what actually happened in the sort of have to take all the evidence and then say, well, this looks like the decay of a Higgs that then decayed the Higgs, that was produced and then decayed to maybe 2 electrons into muons or whatever. So that's what a lot of what is sort of happening. So I think we should be. Oh yeah, so we can show you a few things here that are, let's say, part of the monitoring for the LHC. So what you see here is the plots for something called the beam synchrotron radiation telescope, which doesn't matter what it is, but you can actually see the shape of the beam. So the beam is basically, you can imagine it's kind of a spherical beam that's traveling around the beam, traveling around the LHC tunnel. But this tells us if it's asymmetric. So you can see the X and Y basically, or horizontal and vertical, and then you can see beam 1 and beam 2. So beam 1 in one direction and beam 2 in the other direction. And yeah, it's a bit more complicated than that because we have in the LHC 3,564 potential locations where the beam will orbit. We never use all of them, and right now you can see that there are 3 filled bunches. So it means that there are, well, the bunches is exactly what we call them, and they are bunches of protons. So in other words, in the LHC, we don't have a continuous beam of protons. Instead, they are grouped into bunches. And normally we will have something like 160 billion protons in each of these bunches. So that's a kind of a quick overview. I think we can now, that Sonia is here. Sonia, if you want to quickly introduce yourself.
Yes.
Can you get a bit closer to the mic?
Yeah. Okay. That's fine.
Yeah.
Yes.
Oh, yeah, switch.
Yeah, we can switch.
Sorry.
Yes. Okay. You see my shoulders? You see my face now. Sorry, I was in another phase. I have some echo, but okay, I'll remove just a moment for this. So, my name is Sonia. I do not belong to CMS as Andres, but I like to stay here. So I have to say, for my pleasure that I'm here, and I like to meet people. I'm a particle physicist, and in particular, my background is on astroparticle physics. And now I will be your guide, underground guide, as you see, and I will bring you in the corridors at minus 100 meters. I hope you will enjoy. And now I stop. Okay, and maybe okay if we have the chance later to talk also with the audience, they will ask me if they have any curiosity about me. Okay.
Okay.
See you later.
So let's start heading underground. We have to be done by 5:50. So we don't have as much time as usual.
Yeah. Okay.
But yeah,
Okay. We go straight forward.
Yeah, let's go ahead. Okay, so maybe we can just, as Sonia is making her way downstairs, we can talk a little bit more about CMS. I think we can just go ahead and show this slide. And so I mentioned that in CMS, we have multiple sensitive layers of detectors. So CMS is, you can think of it as a cylindrical onion, right? We have layers inside of layers inside of layers. And you can imagine taking that cylindrical onion and chopping it into about a dozen slices. So in that sense, CMS is modular. CMS opens up into these pills or these slices, as we call them. But you have, I think think of the core of CMS being its magnet. So we have a 6 meter by 10 meter magnet. So 6 meters in inner diameter and about 10 meters long. And this magnet is, it's producing a very strong magnetic field that is really important for CMS, which I will come back to. Maybe we can just go to Sonia for a second. So Sonia, you're muted. Can you hear us? Sonia, you're still muted.
Can you
Good.
hear me?
Yeah.
Yeah, okay. So as I think you already described the experimental HC and where we are, so I will try to stick for the specific things we have here on the experimental zone. First of all, we are already in the on surface, still on surface, but in the experimental zone. And now is the first access that I can do through this door. Now to access, I need to pass 3 checks. One check is the weight, in the sense that the system is detecting that I'm a person. This is an access for people, not for material. And basically I have to step in, you will see, these square of yellow dots, clear dots. So I step in and the system realized that I'm a person. But this is not enough. Then I cannot introduce material, for example, a backpack on my shoulder. So I cannot keep this helmet on my hands. So there are infrared beams that are checking that I don't bring anything else on the, sorry? Yeah, I will say, and only one person, of course, can enter, not 2 persons. Yes, this would be another material. I had a suggestion from the director here. Yes, it's right. And so the second check is the infrared beams. And then there is another check that is a personal check, because of course I open the doors using my personal dosimeter here, just budging here. But there is a second check because this can be even stolen from me. But there is something that I hopefully will be not stolen from me, are my eyes. And so there is a reader for the biometrical reading here that you see, this black box, where my iris will be read by the system. And as they, in the database of CERN, they have a picture of my iris, they will compare and the system will recognize me or not, let's see, and will allow me to enter or not. Now let's try, because I think that the experimental thing is the most interesting. I said I'm an astroparticle physicist, but I'm an experimental physicist. So the door open, I step in, it's already good because it doesn't beep. And now I do my photo for the iris.
Sorry, we cannot confirm your identity.
It didn't recognize me. And now recognize me. Sometimes it takes a little bit more time. And now is also Noemi that is with me. She has to enter, so I have to wait for a moment. She's also bringing the camera, so she has to find a way to hide, if you want, the camera to the system. Otherwise, it will be a problem. But she succeeded as usual. She's very good in this. Yes, she knows how to do. And now she's in, and we enter the second zone. If you would be here visiting with me, this is where the box where we have the helmets for the visitors, very nice orange helmets, but just for rent, not for as a present. You see on the other side, we have other 2 systems to let people entering, because of course you should consider that here there is a lot of work, in particular when we are doing upgrades or there is the stop of the beam, there are many technicians. In the meanwhile, you see the elevator is at -3, so -97 meters. I ask the elevator to come up. In the meanwhile, I tell you that, again, if you would be with me, you could pass two tests of the door, that is the weight test and also the infrared, but you couldn't pass the iris test because, of course, the CERN database has not your iris there. So we should cheat. I could also cheat a little bit the system. That is, I should bring you inside using the door for the material. Now, this door, basically there are two doors. One is on the other side, and one is this one. And usually what we do, we put material in the middle, we close one door on one side, we badge through the doors that you have seen, and then we recover the material on the other side. And now for people, we don't do this. We just open the two doors at the same time in such a way that the people don't have to wait inside. We have now our elevator. We will lose some signal. Andres, he knows very well here. So this fits more or less 40 people, up to 40 people. And we have the levels here. And now we go to the -2, that is -87.9 meters. Okay, we go. And I leave the floor to Andres because I know that it could be that we don't have any signal.
All right, thanks, Sonia. So
Thank you.
in the meantime, I think we can just very quickly show you a few of the other parts of the detector in CMS. So I started to mention or discuss the magnet in CMS, which is again 6 meters in inner diameter. So the point of having this very powerful magnet is that charged particles will bend when they're exposed to a magnetic field. So as they travel through a magnetic field, particles will bend. And you can kind of see an example here. So with this blue curve represents a specific particle that we refer to, that we call a muon. So that's it's exactly like an electron, but it's 200 times heavier. Now, the reason we want the particles to bend that way is that the amount of bending in the particles will tell us about the momentum of the particle. So a particle that has a lot of momentum will basically go straight, right? It's more difficult to change its direction, and we can quantify the momentum of the particles this way. So we have inside of the magnet an almost fully functional detector if you don't care so much about muons. And even, we can still see some, we can measure partly the trajectory of the particles with the innermost part. So we have the innermost layers of our detector are what we call a silicon tracker. So these are many layers of sensors that are similar to a camera sensor. And with these sensors, we basically see many signals in each of these sensors, and we can connect the dots to reconstruct the trajectory of the charged particles. This is, of course, much more complicated when you have many signals, which is almost all the time when the LHC is running. But nonetheless, that's the way that we reconstruct the trajectory of these particles and then deduce their momentum from the curvature. Then we have two layers of calorimeters. Their job is quite different. So here we want to really absorb the particles. And in CMS, these calorimeters are the sensitive material is what we call a scintillator. So these scintillators produce light when a particle hits the scintillator, and the amount of light should be proportional to the energy of these particles. And with that information combined, we can have a pretty clear picture of what happened in the collisions. Now, there's different types of particles that will react in a different way depending on the property of these particles. The property of these particles. For example, a particle that has no charge will not bend under the magnetic field, and in fact, it will not leave any trace behind in the innermost silicon tracker. So we only see, for example, if a photon is produced, a particle of light, it has no electric charge, and it will only show up in the electromagnetic calorimeter. You can have a type of charged particle that we call a hadron, and if it's charged, it will bend and it will leave some signals in the silicon tracker, but it will mainly decay in the hadronic calorimeter. And these type of particles, it's a bit like protons. Protons are made up of quarks, and there's many types of particles that are similar that are produced in the LHC. And so finally, I want to mention the muon again. So the muon, as I said, is 200 times heavier than the electron. That means that it's really, really difficult to stop it. And in fact, we have no chance of stopping the muons that are produced in the center of CMS. They essentially travel all the way through the detector. And what we do is we actually try to bend their trajectories as much as possible, which is harder than an electron because they have 200 times more momentum generally. And so we will see some of the signals that they leave behind in the silicon tracker, the innermost detector, and then they will also deposit some signals in the muon systems. So in CMS, we have a very sophisticated muon system that these are based on gas detectors. I can try to talk about these detectors a bit more later, but for now, we have different types of gas detectors in CMS for these muons. And it also is worth pointing out that outside of the magnet, we have a lot of steel. So we have in total about 12,000 tons, more than 12,000 tons of steel in order to sort of reinforce or redirect the magnetic field lines outside the magnet, which means that inside the magnet, we generate about 3.8, well, exactly 3.8 Tesla. And then outside the magnet, we can generate 2 Tesla. And this is what helps us to determine the momentum of the muons, having this strong magnetic field inside and outside of the magnet. Okay, this is the quickest overview I can give you of CMS. We have a few pictures here of event displays. I'm surprised we haven't heard from Sonia yet.
No. I was fascinating to listen to you.
Okay.
About your explanation. I wouldn't have never stopped you because it was so clear to me. Yes, I was listening. And now I add my part. Okay, first of all, we were talking about muons, you know. So I was showing the logo. We have the muons in the logo just because, in fact, the M stands for muons for CMS. So the acronym contains the muons. Let's say that CMS, as you mentioned, is a detector with a very sophisticated methods to detect muons, but is very excellent for all other particles, I would say, not just for muons. So it's a very good detector. It's a jewel. Now, coming back to the experimental part here. First of all, let me show you. No, this is the -3. Now the elevator is already 1 floor down. But however, we are at -87.9, and I'm in front of the elevator door that should be here in a moment because Noemi, okay, yes, you see. So I'm just opposite to this, in front of the elevator, and this is a safe zone. I'm sure that you cannot hear the sound here because okay, the noise is suppressed with this very good system thanks to Zoltan and that is dealing with this. So, but however, there is a noise here, and the noise is a pumping system pumping the air outside this zone and also the elevator shaft. And this is for safety, because in case of an evacuation alarm, if there is a fire, so you produce, for example, smoke, or as Andres was mentioning, you have a gas leakage, nothing can enter in this zone. So if you would be here with me and you would experience, luckily, the evacuation alarm, it is a visit much more exciting than the normal standard visit, we should come back here and we would be safe here. Also because there are the fire doors. Now we enter inside a real experimental, why it's not working this? Okay, yeah. The experimental side, I don't know why this is, should be. That's fine. Yeah, but it's moving, I don't know why. Okay, so first of all, I would like to show, with the help of Noemi, I would like to show you the surface, just to show you that I'm not cheating. You should see in the middle on the image a rectangle that is a gray rectangle, a little bit lighter than the rest. And this is the surface. And now we are down. And then I show you the -100. That is this floor that you see with these yellow strips on the floor. Now, I'm sure that there is a map that can be shown, but usually I use my hands to do this. We have two caverns. We are really in this way. We have the service cavern where I am, and the elevator is in the middle of this service cavern. We are now moving forward, and the backward part we won't go, is not allowed to go, but this forward part that is behind me, we will step till the end. And then in parallel, we have another cavern, this side, that is shorter than the one, as you see, is shorter and larger. And this is the experimental cavern. Now, there are some connection between the service cavern and the experimental cavern. There are two connections on the sides. We will more or less see only one, and the other one we won't see. And the one, in the middle one, there is this one that I show you. You should see a wall that is gray. It seems to be made of blocks, but there are not blocks. Is just a prism that we pull back, and we can when is not there. Basically, you have a corridor. The thickness of this corridor is 7 meters, because in between the two caverns, maybe from the map you see, there is a wall, a big wall in concrete that is protecting us in the service cavern from what happens in the experimental cavern. Now, we move, we go on the other side. Before I enter, because for me, it's a little bit, there is a lot of noise inside, but just for me, this is called the counting room. There is electronics, is a part of the brain of the detector. We have this room with some electronics, and then there is another room just on the top of this, I call the twin rooms, and with the same electronics, the same amount of electronics. And then there is another room on the other side of this detector that has also the electronics. But these are considered, if you can imagine the brain of the detector, you have 3 levels. One level is the electronics that is attached to the detector. Then you have this middle level that you call the level 1 trigger electronics, and then there is some electronics that is the highest level of electronics on surface. Now we will go through this room of the middle level, and I would like to stop just for 1 minute to show you the wall, what I call the Mona Lisa of cabling, that is related to the muon system Andres was talking just a few moments ago. If you follow me, so what we can do first of all, and this is special, usually we are not allowed, visitors are not allowed to go through the corridors, but as a virtual visit we can. So we can show you some parts of the detector here with the help of Noemi. You can see here are optical fibers, you see here. Of course, we have many of these optical fibers, but also standard cables. I would say that now in the daily life, optical fibers is something normal, but you should consider that all this design comes from with some upgrades, of course, but 20 years ago. So basically, now, I don't think I have to convince you that doing science, it's interesting, but when you do research, basically you live the future, because you are testing using something that maybe in the daily life is still not used. Then it depends. Sometimes you can see this in the daily life very soon, or sometimes you have to wait years to do this. So we are just moving some stuff, as you maybe, I don't know if you listen the noise. Again, optical fibers, many. Please notice also, yeah, yes, computers, of course, normal to say. Notice the cabling. Sometimes it's very regular cabling. Sometimes is a little bit messy, let's say. But however, as you see, each cable has its own label, and I'm sure that people working here, they know exactly everything about this connection. And what you see also are these orange bands. This is a way to say that in case of a power cut, this part is not switched off automatically. So we have to switch it off on purpose, just pushing the right button. Otherwise, we cannot touch, even if the rest is in power cut. So we have this kind of symbol. And then maybe we can go to the Mona Lisa. Now, first of all, you can say, I don't know, this is for me because I did also cabling. This is for me is, I call it the Mona Lisa because look at this wall. First of all, it's red, so it's eye-catching.
Sonia,
But also, yeah,
this
I don't
Mona
touch.
Lisa is it can be an angry one.
Yes,
So
I know, I
be
don't
very
touch it.
careful.
I know.
She might electrocute.
I know, because I just wanted to indicate, I don't know if you can see the number on the top of this number is a 12. So in each of these cables, these are not optical fibers, you have just 12 kilovolts, okay, 12,000 volts. Now think what you have at home. This is just a tiny more, I would say. And this is this is the system to feed the power to the immune system. But okay, please have a look how regular is this cabling. Consider that before doing this cabling, you have to invent the mapping. So there is a lot of creativity. It seems to be a boring job, but it's not. Because first of all, you need to think, to invent the mapping, which cable, which connector to which connector of the cable to which connector on the board. And then you have to prepare the cable. So each cable must be labeled, and then you have to measure the cable. So the length of each cable is different because it shouldn't be not too tight, not too loose. And then you start to cabling. I would say, from my experience of cabling, that when you have done just half of this in one day and you push the switch on button and it works, you just say, I earned my day. You are very happy because you did your job, and you gave some contribution to the experiment. Now we go down, and I reach almost the end of our path, but there are many interesting things to see here. There is this red door that is, this connects to the LHC, but we don't access the LHC from this point because you see it's sealed. This is just for safety, is an escape, you see, only for evacuation. Let's say that we are allowed to open it, but we should have a good reason, otherwise it's not good. And this is when we cannot go back through the path that I was using to come here. This is why, because there is a second elevator here, okay? And this is also one of the reasons why we can stay here. Nobody's allowed to stay underground in this moment in Atlas or Alice or LHCb. Only CMS allows not only people, but also visitors in general to come underground all along the year. So if you come here by chance, you want to visit CMS, you will have always the chance at least to come underground and to visit this place, even if you cannot access the cavern. Now, okay, very fast, because I know that we don't have too much time. I know that you are university people, but we wanted to try something with Noemi, one that we know that it works, and one that we don't know, we want to try. So I will try both. So we have 2 detectors of magnetic field, are very, very professional, I would say. And they are very, very expensive, as you see. So this is to show you that, of course, you need money to do experiments, yes, but you can enjoy physics in general, even just having 2 chains, simple chains. Now, I was told that the magnetic field is on. I don't know. I'm an experimental physicist. I want to check. Let's see if we have the magnetic field. Okay. Now, I know that one of them, it works. I don't know the other one. Let's see. I think that you can see already the chain, what is starting to do. I don't know. The other one. Not yet. Maybe also the other one. Yes. But the chain is reacting better. You see that also now the chain of clips is reacting much better than the other one. This is also bending, but not too much. Okay, so you know what I do, Noemi? I do in that way. Let's see if it bends. Yes. It's moving too much. I don't know why. Look, I'm trying this with you. I never did. I'm just enjoying. Because after you have studied theoretical physics, you like to enjoy with the chain eclipse, you know? Now, look, this is much more evident, you see? And this is because if I could make this wall that I have here transparent, I don't know if I can ask Noemi to go a little bit back to show, you see? Now, let's say that from my position, the detector is more or less, I don't know, about 25, 30 meters at the center of the detector. Yes, maybe the center. Yes, something like that. 10 meters, you say? Even a little bit more. We are in the diagonal. We are just discussing among us. Okay, more or less the order of magnitude is this one. So there is the magnet inside, but we still feel the magnetic field here. And this is the fringe magnetic field. Andres told you that the 3.8 Tesla in the center, outside that you have 2 Tesla, but then on the 2 sides, and maybe when I come up, Andres can explain better why we have this fringe magnetic field. We can feel it. Of course, it's not so intense as inside. It's not dangerous. We can come here, but we can detect it. Okay. And now we can do many things. Okay. I don't know. We can do this, for example, you see, because if you thought that I was the magnetic source, I'm not, you see. Is just alone, and then we can do something else just very quickly. You see, this wall is no magnetic, but these screws, they are. And so look, I have my nice pendulum here. And if you don't want the pendulum, because you don't like a pendulum, I can offer you what I call the magnetic swing, that is this one, where you can just doing this movement. Now this you have to believe me, because I cannot do in a different way. So of course you have the gravity force, and then you have the magnetic field, the magnetic force. But when I push down this chain, there is an elastic force releasing the chain, and I can feel it on my finger. I can feel the chain that is pulled up alone. Is not because I'm just pushing down, but it comes up alone. And this is, you see, is an elastic force. Now
Sonia,
it seems, yeah.
I hate to interrupt, but we only have a few minutes left. We have only maybe 5 minutes.
How much is the time? Yeah.
And I would like to.
Ah,
give-
yes, okay. No, you are right. You are right.
I would like
Can
to give
I-
an opportunity for questions.
Yes,
Thanks
you are
very
right.
much, Sonia, Andreas. So indeed, there's a few minutes for questions. If you guys want to ask anything to people concerned. Questions about paper clips.
Sorry, Andres, to interrupt. This is the butt duck.
Or like that, sir. Yeah, Gabriel.
How would you go about trying to accelerate neutrons to high speeds?
Very good question. So you wouldn't necessarily do, so of course you cannot do it the same way as you accelerate charged particles. So I think we're quickly trying to find an image for you. But Sultan, if you want to jump in, because I'm not sure exactly what image you're trying to show.
Well, I'm just trying to log on.
Mm.
That I forgot to do it before the accelerators.
So there's multiple things that come to mind. And
Oh, yeah.
so when you're trying to accelerate neutrons, for example, what comes to mind for me is a fission reactor. So in that situation, you are producing energetic neutrons. But the point that I'm trying to make is there's many ways to accelerate or give energy to neutrons. That's really what you're trying to do when you accelerate a particle. But what's very difficult is to make them directional. The same problem applies to if you want to make a neutrino beam, right? And neutrinos don't have any electric charge, and even more complicated, they don't interact much with anything. So in that kind of a situation, the way you make or accelerate these neutral particles is you accelerate charged particles and then you do something to them so that they decay into the neutral particles. So a classic example is you hit protons, for example, into a fixed target, and then from these interactions, a neutron, for example, may be created, and then that particle can continue to go in the same direction. So that's a short answer. Hopefully it makes sense.
I think it made sense, yeah. So I guess I would add with neutrons, often we're trying to cool them down and slow them down rather than speed them up. Because with neutrons, you usually want to do a diffraction instead of collide them together. So having like a more focused beam is more useful for that.
Yeah,
which is also very cool. Yeah,
and
has its own
it may be worth pointing out that at CERN we have also, in addition to a world's largest accelerator, we also have an anti-proton decelerator. So we actually have to do this deceleration to capture antiparticles. And that's a very interesting research that's pretty much totally unrelated to the LHC physics, but you can look into if you're interested in that.
Any others, Peter?
What kind of radiation dosage would you get if you were in the experimental cavern while the beam was running?
Well, it depends very much where you are. And let's just put it this way, the areas that are most dangerous, let's say, or with the highest dose, are not physically accessible. So for example, in the forward, so in the end cap regions of our detector, we have a lot of shielding. So this is called, it doesn't matter what it's called, but the point is there's a lot of shielding because this area is rich with neutron radiation, exactly. But you cannot access it. I mean, it's just a giant block of concrete.
Indeed, you can't access the experimental cavern at all.
Exactly. So you cannot physically you cannot go into the cavern with the beam running. There's multiple layers of interlocks that you will trigger. But even if you could, somehow, physically you cannot get to the really hot areas because there is shielding. So you would somehow have to open up CMS and run the beam through, which is not a thing you can even remotely do. But then even if you could do that, I think I know exactly a number that I can give you, but we do have radiation monitors, so I could go over, again, right now, we don't really have collisions right now. But let's just say that closest to the interaction point and the beam pipe itself it's one of the hottest areas, and then in the forward regions. I think even if I could come up with a number, I don't know, I'd have to look up the XKCD with all the bananas for scale. Hopefully you know that one.
Me neither. Something is in back of my mind that probably these are very low values at all, but on the same time they are higher than the legal limits. That's why we are not allowed to be there.
You can actually see Sonia's
showing,
personal
yes.
record. Of
It's
her.
quite new, because it's just 1 month, no, 2 months now that I have it. And okay, this is nothing. Maybe what I can just add is that there is a place at CERN that we can walk on a decelerator, because most of the radiation is just on the
Sonia, just
part.
one remark to the number you showed. This was
Yeah.
something like 30 microsieverts.
Yeah.
The yearly limit here in Europe is 3 millisieverts. Something
this
like
is micro.
1,000 times more than what Sonia already got during the past 2 months you mentioned.
2 or 3
Yes,
months,
2 months. But I was not only in CMS, I was also in AD and the LINAC. So I did a collection of
then it's fine.
places.
Yeah, so I did want to at least mention the upgrade. We haven't talked about the upgrade once. I don't know, Matt, you have 1 or 2 more minutes to spare?
I think we have maybe 1 minute. The next professor isn't here yet, but then we may have to go somewhere. So
Okay, so
maybe we
just
can-
very quickly, so we will have collisions until the end, well, let's say the end of June. And then after that, the LHC will be shut down for about at least 4 years. And so during this 4 years, we will rebuild the innermost parts of the CMS detector. The same will take place in Atlas. From the point of view of the LHC, there's a lot of work that is ongoing and will continue to happen, all sorts of upgrades. The point will be to increase the rate of interactions by a lot. So every time we cross the proton bunches, the LHC was designed to have 25 interactions every time we cross these hundreds of billions of protons. Nowadays, we can go beyond the design and we can get up to 60 or so interactions per crossing. This upgrade, after we come back from these 4 years of shutdown, of a technical shutdown, we will hopefully have something like 250 interactions per crossing. So that is, pushing the technology in many ways. Like, this is the best that humanity can do. And it will be an insane challenge, as you might imagine. And these projects that are ongoing, the upgrades for the inner detectors, for example, these are extremely complicated projects and that are ongoing. Matt, I don't know if you want to add to that, like the kind of work that's going on for the upgrade for you guys, like what you might be involved in.
So I definitely can. So we're working on part of the upgrade for the tracker here, and I might tell my class about that in our next lecture because some of them seem to desperately need to go to their next class. So yes, I think maybe we can end it here, but I would like to say thank you very much to Andreas and Sonia.
Thank you to you.
Brian. Yeah, great. So it's great to see you, and we'll sign off, but thanks very much, and we'll talk to you soon.
Right.
We hope to see you here.
Yes,
Thank you.
next time maybe.
Have a nice
Bye.
day. Ciao, ciao.